Cool. So how many of you are on the LinkedIn platform? Oh, just okay. LinkedIn, yeah. How many use Uber apps? Okay, cool. So yeah, majority of you guys. So I think you guys will be surprised to know that you're already Pinot users. Every time you log on to LinkedIn website, there's reads and writes happening to Pinot to kind of, you know, serve a lot of things, including building a relevant feed for you, things like who viewed my profile and so on and so forth. On Uber, it's things like orders near you and such. And my name is Mayank. I am one of the founding members of the project and currently head the data engineering org at Startree, the company behind Apache Pinot. And I will be walking you through why we will build Pinot, what kind of use cases it's solving for the first half of the talk, and then we can dig deeper into the internal architecture of Pinot, the kind of techniques that we're using to make it fast and serve the queries that it is doing. And then towards the end, we'll have some time for Q&A. So introduction, what is Apache Pinot? It's an OLAP data store. We build it from the ground up. We build its own query execution engine as well as storage format, along with a lot of indexing techniques that we have, and I'll talk about those also in this talk. It's columnar, obviously. If you want to do aggregations fast, columnar is the way to go. It was primarily built or started to serve really low latency, high throughput use cases at LinkedIn, especially things that are applications that are facing members directly. So you have very low error of margin of error there in terms of getting the latencies and the availability and all those things wrong, right? So that therefore it's we built it as a distributed system, highly available, reliable, and scalable. Lambda architecture in the sense that you have the option of ingesting data both from offline as well as real time. You don't necessarily have to do that, but if you do have pipelines, then where the data is flowing in the offline as well as real time, you can just point Pinot to that and you'll be able to make analytical queries on that. It provides a SQL interface for the clients to be able to either programmatically or in an ad hoc fashion query the database. And it's an open source top level project. It's starting to see a lot of adoption in the open source. Here are some of the logos that are kind of like have officially talked about Pinot in some forum or the other that they're using it in production. But there's a lot more than these. We have a very active community in Apache Pinot Slack. If you're interested, I'll highly encourage you to join the community. There's a lot of conversation going on, even regardless of whether you are kind of exploring the technology itself or you are an advanced user and you have some questions around how to solve that. All right, so there's more than 100 companies already using it, more than 250 contributors on GitHub. Close to we're approaching 10,000 commits pretty soon. 3,100 members in the community Slack. So why did we build Pinot at LinkedIn, right? So what was happening at LinkedIn was this is back in 2013-14 timeframe where we wanted to improve the engagement of end users or members and provide them more value for the platform and the app. And the product team came up with this idea that one of the things that's very common for the end user is like they tend to use to go to the page where it's showing like who viewed my profile. And I'm sure if you are using LinkedIn, you probably are visiting that, trying to be very interested in what kind of people are viewing your profile. And around those times, it used to be a bash job wherein if I viewed your profile today, it's going to trigger an event that goes through the ETL pipeline, the dashboard gets updated the next day, and that wasn't really engaging enough for the users. So we said like, okay, what if we, if I view your profile, Sunny's profile right now, he gets to kind of in near real time know about it in terms of the statistics of the counts and the graphs and all those things getting updated in real time. So that was like the marquee use case that we started off with. And obviously this is not your traditional BI dashboard kind of use case. So the challenges here are again, member facing. So downtime is absolutely not, it's a showstopper. And we're talking about tens of thousands of queries for a single table. And you want to maintain P99 of 100 milliseconds or less. So that was one of the first use cases that we solved. And throughput and latency were the more important aspects of this particular problem, right? And then once we did that and we were able to prove it, we were then again able to kind of extend into cases where today, if you log on to LinkedIn, like I mentioned earlier, the feed relevance is actually making read and write calls to Pinot to kind of make it more relevant for you, right? And so once we kind of captured that set of problems, we said like, okay, what next for Pinot? And so we started walking backwards from these really end user facing to maybe the next set of problems, which was more around analytical use cases on the enterprise applications. So LinkedIn has a lot of enterprise applications, and each one of those has a, the enterprise user who's kind of wanting to make analytical queries in an interactive mode. And the problem definition has changed drastically here. We're now no longer talking about 750 million users, but we're talking about people who have the option now to make queries on the fly. They can slice and dice in data on the fly. So you cannot really pre-index everything up front and say, okay, everything will be super fast, right? So here's a slightly different or challenging problem here. The latency throughput goes down by maybe an order or two of magnitude, but data size increases and the flexibility of querying also actually in somewhat interactive manner increases. So we were able to solve these use cases as well with Pinot. And then once we were done with that, obviously, the bread and butter for a lot of the use cases out there is the internal BI dashboards and all. And we said, well, it only makes sense for us to use Pinot for those use cases as well, where all the data that is being collected and generated on the website ETLs through our pipelines to generate KPIs and business metrics that execs and BI folks are looking at. One important thing I wanted to mention here is that we went one step further. It's not necessarily about people who are going and manually looking at these dashboards and charts, but it's also about I want to be able to automatically detect if my KPIs are not doing very well, for example. There was a dip in some particular metric. So first, I want to know about it. Two, I want to kind of do some root cause analysis on this, right? Anomaly detection. So we kind of built that engine as well, which makes queries into Pinot and says, okay, not only do you have the dashboards, but you also have the capability to kind of figure out anomalies in your business metrics that you're tracking and do some root cause analysis. So with this, we kind of covered the spectrum from one end to the other, where the problem space slightly evolves or has different challenges. And traditionally speaking, people end up solving different problems or different buckets of these problems with different systems. Here, where there is something that needs a very high throughput, low latency, folks may go with a key value store pair kind of a store, versus on the other, they may go with a more traditional OLAP. But the power of having a single system, all these problems, is a unique USP that Pinot brings in. Again, at LinkedIn, for deployment, there's more than 100 member using or website-facing applications that are being powered by Pinot, 3,000 internal dashboards which are powering thousands of metrics. The LinkedIn deployment in production is getting about 200,000 read queries per second and ingesting at the rate of 1 million events per second. So that just wanted to give you, some order of scale on how it is operating at LinkedIn. So that's where Pinot originated, and slowly when the project starts to see adoption, Uber was the next big one, and they started using it for slightly different but similar in terms of technical challenges, kind of, right? So I mentioned Uber Eats. If you're using that, the application which powers the orders near you is one of the many examples that's being powered by Pinot. Again, this again is the dashboard here is not really a BI dashboard, but more of a dashboard that is given to the restaurant managers, where they get this power of being able to make the business critical decisions in real time, because they get to monitor how their orders are doing in real time. If they're low on inventory, if their orders are going late, and so on. And this is really important because they don't have to wait for a day or half a day or several hours to get to know about it. And knowing it now is a huge operational efficiency win for them, is a huge business proposition for them. So that these are the kind of use cases this kind of enabling. And obviously there's the the dashboarding and the exploration use cases as well. The scale there at Uber is about 15, well, somewhat dated, but 15,000 read queries per second. Their data freshness, they want to keep it at 30 seconds or less. I believe they use Kafka internally. And P99 for the read latencies, they want to keep it at 100 milliseconds or less. Last in this category, just to give you an idea of the versatile and the wide variety of use cases Pinot is powering, right? So one of the things that I like to talk about is the use case at Stripe. I hope folks are familiar with the Stripe, the financial company. It's a fintech company. So what they had was essentially every transaction that happens on the Stripe platform actually is being stored in a ledger. And they had use cases where they wanted to be able to do few things on that data. They not only want to do analytical and ad hoc queries, but they also wanted to build BI tools. But most importantly, what they wanted to build was something like a ledger balance check, right? So these transactions are happening. At the end of the day, you want to make sure all the money adds up. And if there's a discrepancy, you want to know about it within a few seconds or maybe a couple of minutes, and not tomorrow when it becomes a lot more costly to know about it, right? So their system looked like this. They had like 4 or 5 different systems, key value stores, an ETL job, and all those things happening and powering these kind of systems. And they ventured into using Apache Pinot in the open source, and they were able to kind of simplify their use cases where all of these use cases on the right-hand side are being able to solve through this architecture where Apache Pinot sits in the core of the platform. Scale-wise, 1 petabyte of data is what they have today. They have close to 1 trillion transactions that are all stored in Pinot, and they look for sub-second latency for the P99. Right. So I mean, that was mostly to give you brief on what's the problem space and what are the different challenges and how Pinot's, where Pinot is actually solving it. But for the rest of the talk, let's focus more on like how Pinot is solving it and dig a little bit deeper into the architecture and so on. I'll go. Yeah.
Can I ask you a question?
Yes.
Can you go back? So, in this Stripe, can you go back?
Oh, sorry.
Using Presto to query Pinot.
Yeah.
How much overhead does that add?
Yes. Great question. So essentially, let me just repeat the question. The question is, they're using Presto to query Pinot, and how much overhead that. So before I answer that, let me give you the background on what the use case here is, right? So because Pinot is an OLAP system and was built primarily for more interactive queries, we had in the past shied away from doing things like long-running joins, for example, right? But there is a wide variety of use cases out there where they say that, well, I don't want to do like 10 tables join. I want to do like 10 million rows with a 10,000 rows join, so that I can do something as a data scientist. I can do something interactively, right? That's the use case. So we went ahead and built a connector for different versions of Presto. There's PrestoDB, there's Trino. All of those have a dedicated connector to the Pinot system. And the reason why it doesn't add, the philosophy there is the following, right? The connector is smart enough to figure out that, oh, this is not a generic data system under me. This is actually a SQL engine. And I, as a connector, am aware of its capability, so I can push down as much as possible to Pinot. So if a query that could have been fully executed in Pinot, there's minimal overhead. It just completely gets pushed down.
So the reason you're using Presto is because of the join.
Yeah, yeah. In this particular case, yes. Yeah, so let's talk about the different blocks in the architecture of Pinot. There's the Pinot controller. This, you can think of it as the brain of the system, which is doing a bunch of things like, managing the state of the distributed system. More specifically or more concretely, things like it's making decisions on when data gets pushed in, which server that should particular shard go in, and so on and so forth. Beyond that, it's also managing providing an admin API for building things like CRUD operations like creating, deleting a table, and so on and so forth. Right. The second important component is Pinot Broker. Essentially, you can think of it as a gateway to Pinot to be able to query it. It's just a REST endpoint where you will fire in your SQL query either manually or through some REST API. And Broker is responsible for compiling the query, figuring out which servers to scatter the query to, gather the results, do the aggregations, and return the result back. Pinot servers are the guys who are actually hosting parts or shards of the data or partitions of data, and responsible for running the query that came in on the data that they are hosting. There's two kinds, offline and real time, and that just means like what kind of data they are hosting, data that's ingested through offline pipeline versus real time. And for the most part, the code is the same. The only difference is real-time servers are also responsible for ingesting data directly from the stream, indexing it on the fly, and committing it to the system. And just one call out here is that there's no like micro batching happening in memory. As soon as an event is ingested in Pinot, it's immediately available for serving, for example, right? So there isn't any freshness latency issue there. And then last but not the least, we have an optional component called Pinot Minion. You can think of it as a framework, logical as well as physical framework for doing background jobs. And some example of these background jobs are, I have this data set. I also have to be GDPR compliant. So go ahead and do all the PII stuff and GDPR stuff there. So that may be a background job that you can configure to run. Other examples are, I have too many tiny Parquet files that flew into the system. I want to be able to merge and roll up to make these smaller ones into bigger ones purely for performance optimizations. Those are tasks that a Minion can run for you, for example. Yeah.
So for Zookeeper, Zookeeper has its own problems when you have hundreds of thousands of queries coming into the system.
Yep.
Does that become a bottleneck?
No. Yes, so great question. So let me explain or zoom in a little bit into what are these components, right? So Pinot controller is the brain of the system, which is maintaining the distributed system itself and making all the decisions. The way it does is it uses Apache Helix. It's another open source project built by some of our team members only. And Zookeeper there is used mostly for a couple of things. One is metadata store, like what server is hosting what data kind of information, how many tables there are. And also kind of the change notifications, right? Like, okay, the controller decides server A should host shard B of the data, then Zookeeper kind of ends up notifying the server. Now, given that, so the way we use Zookeeper, we have optimized very heavily on reducing the reads and writes on Zookeeper. It's only on the control plane. There is no queries in the, the read path does not interact with Zookeeper. So our reads and writes to ZK is very, very minimal. So we are nowhere near that being a problem. Yeah, so I talked about use cases that are kind of very, very high throughput and low latency. So let's talk about like what is making Pinot really fast, right? So the way I kind of talk about it is that when we designed Pinot, we looked at both ends of the spectrum. The high level design, we wanted to make sure that's a very scalable architecture. On the other end of the spectrum, we said, okay, let's also do all the low level optimizations. So that we can squeeze the most out of a box, a single node, and then we just scale it horizontally. So what that means more concretely is that we've kind of like built our own storage format, which is optimized not just for storage, but we also have techniques to kind of make the scans really fast And some examples are, it's a columnar store. We know we are going to process blocks by blocks. So we have written very tight loops that can vectorize, that can do vectorized reads. And another example that I like to talk about is, think of, a particular column with a cardinality, let's say, 100 billion rows, but the cardinality of the column is only 1,000. So you only need like 10 bits to store each one of the individual values, which means when you have to read like a few blocks of these, one way, the down way to read is, okay, I'm going to read 11 bits per disk seek. And that obviously is not a great idea. So what we have done is optimizations where we read, word by word in parallel, and then, do the bit manipulation in memories just to make the I/O, reduce the number of disk seeks. So that's what I call fast scans at the lowest level, but we also do smart scans. And what I mean by that is our philosophy in Pinot is no matter how much your data size is, you may have like, one single table which is a petabyte of data, but we want to only scan the data which is relevant for this query. That's our kind of philosophy. And for that, we have built a lot of, rich set of indexing schemes that helps us eliminate or prune out data that doesn't need to be scanned. And that's what kind of like makes it fast. We also, if the data is partitioning is another one. Pinot does not impose the restriction or requirement that the data has to be partitioned, but if it is, then it will make use of it. We also maintain metadata at different levels, like for example, the server level, the shard level, and the index level, and so on. And at every level, the query execution engine will see, do I need to look at this data or not? And that's just one metadata lookup, and these kind of tricks make it really, really fast. There is another index that I want to talk about specifically in the coming slides, which is called starter index, and you can think of it as a way to configure to your suit or need how much you want to pre-aggregate or pre-materialize some of your query answers, right? And I'll talk about that as well. Yeah.
So I just want to know like what's the data format? Is he local storage or is he on cloud?
Yeah. So the data format is essentially Apache Pinot's own format. So it's a columnar store. So we build our own format, and that data is, once you have a physical file, the architecture is that the serving nodes, if you want really fast latencies, can cache the data locally on their local disk. But we have also built systems where this data, this can be tiered. So a lot of very common use cases, I have 5 years worth of data. Most of the time, I query only 1 month of data or 1 day worth of data. So you can tier the storage of the data, saying, okay, the most recent data can be stored in fast local disks, and the others can be in some deep store, blob store like S3 or somewhere, right? So the format itself doesn't impose where it should be stored, but there is a concept of tiering which will help you optimize cost versus latency on how fast you want to access and how much you want to pay for it.
I see. So Pinot does have like a hierarchy of storage.
Yeah.
Hot,
Yeah.
relatively hotter.
Yeah. And it's a lot more than lazy loading. It's not dumb lazy loading. What we do is a lot of smart techniques like prefetching the data, right? So it figures out, looking at the query even before the plan happens, that I might need some metadata or pre-indexes for these kind of columns, and start pipelining those fetches while the planning is happening. And it's a hit and miss, but the whole IP is around how often you actually hit.
I would mention
Yeah.
the first part of it. So does Pinot has like an interface like Seiko?
Yeah.
Okay. So did you anything special for execution plan?
Yeah.
Because you have Seiko.
Yes. So we have built our own query execution plan. While since up until recently we hadn't really worked on join, so it's an aggregation group by top end kind of queries, right? And so our plan is smart enough. It's not as sophisticated as a plan or optimizer that would be needed to plan out let's say like an n-way join. but we have smartness for the queries that we support. And what I mean by that is, let's say you have a very complex predicate on where a equals 1 and or this, that, blah, blah, blah. It will parse it and figure out these columns have indexes, and within those indexes, this is the most efficient index, so I should apply that one first. And then the output of that is kind of like cascaded into the other one so that you avoid kind of scans, right? Does that answer your question?
Okay, that's all.
All right. Yeah, so most systems end up having something like a sorted and inverted index, but we've also built for range queries. If a lot of these OLAP queries are where time between now and 3 months ago or something like that. So we've built like indexes that can help you with that. Bloom filters, obviously, but those are more around how to make a query predicate execution fast. The other indexes that I'm going to talk about are more around, now I'm able to enable different kind of use cases. I'll talk about those as well. So before I go into the more advanced use cases, let's just talk about very simple use case, right? So let's say you have a website and you want to count how your website is being viewed, and in this particular case you want to say, okay, I want to know all the website accesses from Chrome in the US, right? So typically you will have, you look at any system out there, there will be a storage component that will be used to kind of scan the data, then filtering, and then aggregation. That's how you kind of plan this query. Not there much to it. And most common technologies on the storage layer would have something like a columnar store, and they'll do some dictionary encoding, compression, and things like that on the storage layer. On the filtering layer, they will, if it's a simple system, it will just end up scanning everything, right? And then on the aggregation, again, they end up having scans. But specifically talking about OLAP systems, inverted index is a very common thing where you kind of maintain an index saying this particular value appears in records X, Y, and Z, and therefore I just need to go there and just read those. So that's a common technology. But what makes Pinot better and faster just for a simple query like this is things like sorted index and star tree index, which I'm going to talk about next, where it's not only helping the filtering part, but it's also helping the aggregation part. Right, so I mentioned star tree index multiple times, so let's zoom into what this is. So on the lower left side, the blue one, you can think of it as your data is already indexed in Pinot, and then on top of that, we build an auxiliary data structure, which looks like which has two parts. One is a tree structure, and the other one is on the bottom right is the aggregated docs. And so what happens is every level in this tree is a dimension split order. And so when you're walking the tree from top to bottom, following the arrow on the leftmost, you're saying where country equals Canada and browser equals Chrome, these are the set of records that I'm interested in, right? So yeah, so it's kind of like an inverted index, not really that interesting. Where it starts getting interesting is, okay, my query is I don't really care about what country, but I want to figure out all the access of Chrome, all Chrome accesses, right? So then in the regular flow, okay, some Chrome here, I'm going to scan these blocks, then these blocks, and these, and so on and so forth, which obviously is not efficient because you're increasing the disk seeks and so on. The query that I just mentioned, where I don't care about the country, but I want to count the browsers, is the star node on the first level on the rightmost, right? Since I don't care about the country, I'm going to take that path, and then I follow the Chrome, and all of a sudden, I have the answer right here, right? So that's kind of like the idea where you are kind of helping the query not only in the filtering phase, but also kind of aggregating the answers. Now on the one extreme, you only have the lower left block where nothing is pre-aggregated. On the right extreme, every answer to your query is a value lookup, and that's where it becomes key value store. The beauty of this particular index is this highly configurable, that you can define what queries you want to optimize and to what granularity, right? And So you may have a data, a lot of times what happens is, okay, I have a data set, I have 100 queries that I run, 80–90% of them are very high selectivity, few of them are very low selectivity, which are very, doing some count distinct 100 billion rows, for example. And these are the queries that you want to set up the star tree index to make faster, to avoid having to scan the, not only avoid having to scan the raw data, but also have the pre-computed answer at different levels available, right? So that's kind of like the beauty of this particular index. Yep.
How's the aggregated data stored?
Yeah, so the Pinot's segment, we call there's a segment, and it's nothing but a set of contiguous rows, and it's a columnar store for that, right? And so it's essentially, you can think of this particular column, these are the dictionary values, and these are the dictionary IDs for each one of the rows, right? And so that format is not different between the raw and the aggregated. So it remains exactly the same. So the readers and writers in the code upstream, they don't really care whether I'm reading from, the planner will hook up the right thing, and the whole query execution just works without having to worry about what index it is, right? So that's the beauty of the code.
But in that case, like since you separate the real-time server and the offline server, how do you update this data?
Yeah. So this particular index, so let me talk a little bit about how real-time ingestion works in Pinot, right? So the way real-time ingestion works is you tell the real-time servers, this is the coordinates of the stream to ingest data from, and it will start ingesting, and it will like shard the data and so on. But a row, when it is ingested, it's kind of like semi-indexed in memory for some time, so you kind of have batches, but every row is immediately servable. And periodically, you take this in-memory index and flush it onto disk, and that's when this indexing can work, right? So typically, you may have a 2 years worth of data in your hybrid table, but this is only the 3 hours that data is in memory that you don't have this particular index, but 99.9% of the data has this index, right? So the query can still be super fast.
So the assumption is that this aggregated data could be stale, but it will eventually digest.
Yeah, so it could be stale, but the query is still answerable from this section, but only for a very tiny portion. Therefore, you don't pay the amortized, latency is very, overhead is very small.
A follow-up question. So do you build the star tree index at the level of segment or time chunk?
There's a level of segment. Yeah. So I think I'll have to like speed up a little bit. We have 5 more minutes. I think I can just, so I think here what I wanted to show is this star tree index is really, configurable for your liking. So you can say, I want to pay 10% more storage overhead. And so I have that wiggle room to pre-materialize 10% of the answers. Versus no, I don't care about storage costs. I'm going to pre-materialize everything because I want to answer everything in 1 millisecond or less. And this particular data structure gives you that option to customize it for your application, for your needs. Talking about more specialized indexes. So far we've only talked about how to make filtering fast, how to make aggregation fast. But let's talk about how to enable new use cases. When we saw Pinot's adoption, new kind of use cases started coming in, and some of them were like, I don't have fully structured data. I have like 5 columns that are fixed, but there is like some data which is somewhat schema-less and so on. How can you help, right? So there what we did is we kind of like build this JSON indexing where you can have a particular column as a JSON blob, and we index every leaf level value in that blob. So you can, in this particular example, make a query like, give me all the people who live in First Street, for example. And without the index, you would have to scan a lot of data, deserialize the JSON, and bunch of stuff. You see like 17 seconds versus it becomes a really simple 10 millisecond query just with this index. The other one is texting less again. So the use case here that we started seeing is more around security and all, where we say, okay, we have tons and tons of logs. I want to see which IP addresses are making access to this particular service or API, right? And that's a very typical security use case. And what that means is I'm going to have to scan all the logs, figure out the, tokenize everything, and do like a text indexing and all. And so that's kind of, that whole thing is inbuilt into Pinot. And you can say, every IP address which follows this particular category, give me the count of those. Or say, I'll give a count of all the exceptions which have this keyword or that stack. These are the use cases that start, getting enabled by Pinot. Yeah, so I also wanted to mention something about Upstart since we are in the HTAP conference. So there is definitely a need for being able to so OLAP systems are primarily immutable, and when they say they support mutability, they just mean like, okay, you can update a segment or a time partition in its whole, not a single row in that time partition. With this feature, you can actually in real time go ahead and update a single particular row, or as long as you have set it up right with a primary key and all, and there's a way to identify that row, this feature will give you that capability. And the use cases here, again, I mean, I don't have to kind of explain that. We are in the right place for that. Is, simple example would be a Uber transaction happens twice. Once is when kind of like, the initial bill, and then when you add a tip, there is another transaction to kind of adjust for the bill. And those are all, the use cases that get solved by this. Tiered storage, I think I already covered during your answer, right? So your question is basically, again, giving you the flexibility to say how much cost you are willing to pay for the latency that you want, right? That's kind of the philosophy here. And last but not the least, so one thing that I mentioned earlier on was that because we were designing Pinot for high throughput, low latency systems, we shied away from joins up until recently. But what we are seeing is a lot of such use cases where, for example, we had to use Presto is, yeah, I'm not really looking for a full SQL engine which does like a join that runs for half an hour. I'm looking, I know my data, the inner tables are so small that this is still going to be interactive. That's one use case. Another one is, I want to visualize this data using Tableau and Looker and so on, but your system is not fully SQL compliant, for example. So I can only push down some of the things and not others. And once we saw enough of those, we are rewriting our query execution stack completely from a single stage scatter gather to a more of a multi-stage query execution engine. A lot of very interesting work happening there. There's a talk about it. There's a blog about it. If you guys are interested, you should be able to find it. And so that's something that I just wanted to call out to say like what we're doing here. And yeah, so finally, in essence, what I wanted to say is we started off building Pinot to solve very niche, very particular through high throughput, low latency use cases. But once it saw the success there, we have been able to transition it from that end of the spectrum all the way to the interactive use cases, and now further on to the more join kind of use cases, as long as it's in the interactive domain. So yeah, that was my presentation. Hopefully you guys learned something.